All right, class, I'll try another solution here. How about chapter 3, number 28? It says a daredevil is attempting to jump his motorcycle over a line of buses parked end to end by driving up a 32-degree ramp at a speed of 40 meters per second. How many buses could he clear if the top of the takeoff ramp is at the same height as the bus's top and the buses are 20 meters long? So a picture might look something like this. We've got this takeoff ramp, and as they said, 32 degrees. And then we're going to take off at 40 meters per second. Then we're going to line up these buses. And so I'll draw one bus, two bus. And at least for a moment, you might think about a long line of buses. Because to answer the question here, how many buses can he clear if the top of the takeoff ramp is at the same height as the bus's top and the buses are 20 meters long? So why don't we take this to be the launch point and then also take that to be the origin? And so the path looks something maybe like this. And I won't say that there's just two buses, but there's a bunch of buses, and then he would land on this next to last bus. And of course, if you removed that bus, then you would land all the way on the ground, or maybe you'd put a landing ramp there or something like that. And so why don't we do this? Why don't we see how many 20 meters we have? And then we should have a bunch of 20s and a little bit more where the cyclist comes down, and that would answer our question, how many buses? So that's kind of the strategy here. And so notice that this problem's a little bit harder than just a simple question of, how far does a motorcycle go? It put a little creativity in here and makes you think about, all right, how am I going to figure out how many buses this is? And so that's what makes the problem kind of a step harder than just a simple, how far did it go? But ultimately, that is the question, how far did it go? So let me do the same thing that you've seen me many times, and maybe I'll just do a little bit faster now. But the starting positions are 0. The accelerations are known because it's 0 in the x and 9.8 in the y. The initial velocity in the x direction then would be 40, the cosine of 32. And the initial velocity in the y direction would be the 40 times the sine of 32. And maybe one quick comment, right? If we made a little triangle over here, we can then call this a 32. And if this is the initial velocity, this would be in the x direction, and this would be the y direction. And so something like cosine of 32 would be initial velocity in the x over the total initial velocity, which is the 40. And that's how I got this number. And instead of doing the trig again, since we've done it quite a few times. All right. And same thing here. You would just have a sine in there. And it might be useful to even have a number moving forward. So let's go 40 times the cosine of 32. And that would be 33.9. And over here would be 40 times the sine of 32. And that would be 21.2. All right. So there is my starting conditions. And then taking the standard equation for position and recognizing that the initial position and the acceleration is 0, my equation for the motorcycle's position in the x direction becomes this. And so I've got this time and the horizontal distance. Whereas in the y direction, it would look something like this again. where again, we would call that one 0. The initial velocity in the y direction is that 21.2, and the 1/2 of a negative 9.8 is a negative 4.9. And in this case, let me put a 0 to figure out then where they land, because when the motorcycle lands, it would be at the same height they launched, and that would be y equals to 0. So where the motorcycle lands, I know it's y. I don't know it's x. In fact, that's what I'd like to find. It's x. I could figure out how many 20s fit into there. So if you look at this equation, I can then solve for time, and then it is a simple factoring out here of one of the t's, and so I've got two factors, which means equal time equals 0, and as we mentioned on another one before, that's hopefully obvious why it's an answer. At time equals to 0, it does have a height of 0, and that's where the cyclists take off. It's the other solution we want. There's another moment in time greater than 0 where the motorcycle would have a 0 height also, and so that must be the solution we're interested in. So it would be 21.2 equals 4.9 t, or t equals, and so I will go 21.2 and divide it by 4.9. And so it's about 4.33 seconds that the motorcyclist is in the air, okay? Now, maybe this would be a good time to say something that I've been saying now that I've done quite a few solutions here from Chapter 3. Notice what I'm doing. Notice that it's the same basic principle. This is a chance to say that physics is about knowing how to apply a few but powerful fundamental principles to explain a universal phenomenon. And so just breaking down it into its vectors and treating x and y separately is what I've been doing on these problems over and over and over again. And that's the fundamental idea. So I start with that idea, not much to memorize, maybe a little tough because it's mathematically involved, and you guys might be still working off the rust spots on your math. But as we're doing the math, I hope you see it's the same logic. And so give me any problem in this chapter, and I'm sure I'm just going to, make an XY column and talk about its X motion and its Y motion, and then I can just go through a bunch of deductive reasoning. So I can get any motion I want. It's just deductive reasoning here from a few simple but powerful concepts. All right, well, using that time and putting it into the equation for X, I can now answer how far does the motorcycle go in the X direction, and it looks like 146.7 meters. So if we now divide that by 20 to find how many buses it is, so maybe I should stop right there. Again, if the problem just said divide by 20, that's an easy problem. But it said how many buses, and so you have to know how do you calculate how many buses, and that's where you learn that 4th grade division. You always ask how many little things fit into the big things. That's what a quotient is. So if you're asking how many buses fit into this total length, it's your reaction is to say, oh, that's a division problem. All right, so I'm going to do a division problem. I'm going to see how many 20s fit into here, and it turns out that a little over 7 fit into here. So it looks like 7 1/3. And so that answers the first part of the question. How many buses? 7. And so it doesn't match my picture exactly, but imagine 7 buses here. And this being the 8th bus, this is going to come down at about a 1/3 length on the 8th bus. That's what this 0.33 is, 1/3. So we clear it by 1/3 of a bus. And that is kind of what this last part is asking. It says, discuss what your answer implies in terms of the margin of error. And they talk about your range and your horizontal distance. So to make the 7 buses, you got to make at least 140 meters. And this speed and angle, you should be going 146.7. So you have an extra margin of error of 1/3 of a bus, or 6.7 meters, whichever way you want to say, what is my extra forgiveness? So if the motorcycle rider takes off and they don't quite get this right, maybe their speed is a little too low, or the ramp angle is a little less than anticipated, you're gonna go short. And you got a little playroom here. You've got 6.7 meters. And so if things aren't exactly perfect, you don't get up to this speed, but you do get, almost there, and so you only miss this by 3 meters, you're still fine. It's when you go too slow and you miss it by 7 meters is when you're going to clip the 7th bus and the back of the bike and crash, perhaps, depending on how they build this. So a lot of them have a ramp on the last ending one. So if you do come up short, you end up making a hard crash on the bus and then down the ramp. But better to land on the landing ramp there. All right. Hope that one helps.